Hello and welcome to this revision session on A-Level Physics Paper 1. So in today's revision session we're going to look at how to answer examination questions on A-Level Physics Paper 1. So if we've been successful and learned in this revision session, we should be able to answer A-Level Physics examination style questions, assess your understanding on A-Level Physics, and finally understand what topics you need to improve upon for A-Level Physics. So for this revision session, what I suggest you do is when completing your work, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in the left hand section write down your working out or answers to the questions in the revision session. When doing this, make sure you write in full sentences and show your full working out, whilst in the right hand side of your page, in this section write down any pieces of information which you find useful or any hints and tips on answering the question you've gained from this revision session. And after the end of the revision session, write up these notes into a revision sheet for you to use independently. Now, how should you be revising your A-Level Physics? Well, you should be independently revising A-Level Physics, and to do this there are three key steps in this revision process. Step 1 is learn the key facts of the course, so use things like revision guides, class workbooks, prep notes and the textbook to learn the key ideas of the course. You may wish to make mind maps or to write out notes yourself. The second step is to test yourself, to retrieve your knowledge. So use things like Caboodle, and Seneca, and knowledge checkers to quickly test your own knowledge, and you may wish to do this from your own cue cards. Then finally, step 3, you practice examination questions. So use examination preparation books, homework books, study books, additional workbooks to help you answer examination questions and then mark your own work. Now you may wish to download your own examination past papers to do this. So the three steps of learning the key facts, then testing yourself, and then practicing examination questions are the way I would suggest you independently revise A-Level Physics. So let's have a look at step 3 now. Practicing examination style questions. So the first topic we're going to look at is particles and radiation. So in the following question, figure 8 shows a photocell which uses the photoelectric effect to provide a current in an external circuit. Electromagnetic radiation is incident on the photoemissive surface. Explain why there's a current only if the frequency of the electromagnetic radiation is above a certain value. Then state and explain the effect on the current when the intensity of the electromagnetic radiation is increased. So pause the video now and then unpause the video when you want to go through the answer. Right, so the first idea is we need to understand what is going on in the photoelectric effect. Now the photoelectric effect is proof that light acts as a particle, so it links into the energy of the photon. Now the photon is a key word here because it indicates you know light is a particle. Now we know that if the energy of the photon is greater than the work function, electrons are emitted. Now remember, the key principle of the photoelectron effect is that one photon can only be absorbed at a time by an electron. So if the energy of that photon is not enough to overcome the attraction to the nucleus, the work function, the electrons don't get emitted. Now the next question, state and explain the effect on the current when the intensity of the electromagnetic radiation is increased. Well, again, remember, what do we mean by intensity? Well, intensity means how many photons hit the surface in a particular time per second. So if we increase the intensity, more photons are incident every second. So this means that in the one-to-one interaction of photons to electrons, there's more photons absorbed by an electron per second, so therefore more electrons are going to be emitted. Now we can say that more electrons are emitted because we already know that electrons are being emitted from the previous question, so we can state that fact. Right, let's now have a look at another question. A student investigates the property of the photocell. The student uses a source of electromagnetic radiation of fixed frequency and observes that there's a current in the external circuit. The student then connects a variable voltage supply, so the potential terminal is connected to the electrode with a photoemissive surface and the negative terminal is connected to the wire electrode. As the student increases the supply voltage, the current decreases and eventually becomes zero. The minimum voltage voltage at which this happens is called the stopping potential. Now the photoemissive surface has a work function of 2.1 eV. The frequency of radiation the student uses is 7.23 times 10 to the 14 Hertz. So calculate the maximum kinetic energy in joules of the electrons emitted from the photoemissive surface. So pause the video now, then unpause the video when you want to go through the answers. Right, so the first thing to note is we need to know the equation for the photoelectric effect. So that is HF, the energy of the photon, is equal to the work function plus the kinetic energy. So therefore we can rearrange that and say that kinetic energy is equal to HF minus the work function. But the next thing we notice is the work function is in EV. Now we don't work in EV, we work in joules, so we've got to convert from joules to EV. And as shown here, the conversion factor is 1.6 times 10 to the minus 19. That's a really important conversion factor, so I would suggest you memorize that value. So therefore we can work out the photon energy by doing H times by F, then subtract that work function to give us our kinetic energy of 1.4 times 10 to the minus 19 joules. Let's have a look at the next question. The student increases the frequency of the electromagnetic radiation. Explain the effect this has on the stopping potential. So pause the video now, then unpause the video when you want to go through the answers. Right, so what do we know about the frequency? Well, the frequency affects the energy of the photon. E equals HF. The only factor that affects the energy of the photon is going to be the frequency. So what we can say is if we increase the frequency, we increase the energy of the photon. So because the photon has more energy and the work function is a fixed term, this tells us that if the photon energy increases, the kinetic energy of the photoelectron is increased. The electrons are emitted at a faster speed. There's the same number of them because it's one photon to one electron, but they're moving now with the faster speed. So that tells us the potential needed to stop them is going to be larger. So because the energy of the photons is greater, then the kinetic energy of the photoelectrons is therefore larger, therefore the stopping potential will be greater. Let's look at the next question. Helium is the second most abundant element in the universe. The most common isotope of helium is 4-2, and a nucleus of this isotope has a rest energy of 3,728 MeV. In 2011, at the Relativistic Heavy Ion Collider, anti-helium nuclei were produced. Nuclei of anti-helium are made up of antiprotons and antineutrons. It suggests that an antineutron can decay to form an antiproton in a process similar to the beta-minus decay. In one particular collision between an anti-helium nucleus and a helium nucleus, the nuclei annihilated and two photons are formed. Firstly, state what is meant by isotopes, and then explain why two photons are formed instead of a single photon when a helium nucleus annihilates with an anti-helium nucleus. So pause the video now, then unpause the video when you want to go through the answer. Right, so you've got to know the key definition of isotope. It's something you've just got to memorize. You've just got to learn it. So remember, it's isotopes in terms of protons and neutrons, or atomic number and mass number. Isotopes are nuclei or atoms with the same number of protons or same atomic number, but different numbers of neutrons or different mass number. Now the next thing, why are two photons formed instead of a single photon when the helium nuclei annihilates? Well, remember, annihilation is just a collision. So what is always conserved in a collision? Well, momentum should be conserved in a collision. Now because we have a particle and antiparticle coming together, they're going to have equal yet opposite momentums. So the total momentum before is going to be 0. So the total momentum afterwards has to be 0. So the only way you can get a 0 momentum value for two moving objects, the photons, you're going to have two of them go to the opposite directions. So therefore one's a positive momentum, one's a negative momentum, and they'll cancel each other out. Let's look at the next question. Complete this equation for the possible decay of an antineutron, and then what interaction will be responsible for this decay. Pause the video now, then unpause the video when you want to go through the answer. Right, so first thing you've got to remember is, okay, the antineutron to the antiproton is going to be very similar to the idea of your beta decay. So in beta decay, you can get a neutron going to a proton, and that would then make an positron, then you would have a antineutrino as such like this. However, okay, we can still work it through. So what we can do is we can say it goes to the positron like that, and it produces your neutrino. Now, it's always important to note that when you produce a lepton, the anti-lepton neutrino will also be produced as well. That's to conserve the lepton number in the process. So for example, if an electron was produced, well, an anti-electron neutrino would be produced on electron antineutrino. Now in this case, a positron has been produced, an anti-electron, but we tend to call them positrons. So therefore, what you've got is you've just got the standard electron neutrino, because it's when you got the antiparticle, you get the neutrino, and when you have the particle, you get the antineutrino. Right, so what interaction is responsible for the decay? Now here's an indicator. If the decay involves both hadrons and it involves leptons, it's going to be the weak interaction. If it involves a quark changing flavour or type, it's going to involve the weak interaction. And if the strangeness isn't conserved, which isn't the case here, but that's just something for later to think about, it would also be the weak interaction. Now if we look at our decay, we've got neutrons and protons, which are hadrons, and we've got a positron, and we've got a neutrino, which are leptons, indicating to us it's the weak nuclear interaction. Also, because the antineutrons turn to an antiproton, quarks must be changed in flavour, another reason why it's the weak interaction. Let's look at the next question. Deuterium is an isotope of hydrogen. It contains one proton and one neutron. Calculate the specific charge of the deuterium nucleus. So pause the video now and unpause the video when you want to go through the answer. Right. You're not given the equation for specific charge in the equation booklet, but if you remember the phrase specific, or you look at the units, you can work out what the equation is going to be. Specific means per mass or per kilogram. So therefore, the specific charge is going to be the charge of the nucleus divided by the mass. Now again, remember, it's the nucleus, not the atom. So therefore, we will have an overall charge. So what you would do is you would know the deuterium nucleus, which is an isotope of hydrogen, which is one proton. So therefore, the charge is going to be one proton's charge, which is 1.6 times 10 to the minus 19. Always important to note the charges of protons and electrons in coulombs. Then you divide it by the mass. Now there's one proton and one neutron in deuterium, as stated in the question. You can then look in the equation book to find your masses of protons and neutrons in kilograms, which is given on the screen there. There you do the charge divided by the mass, and you get 4.8 times 10 to the 7 coulombs per kilogram. Next question. The proton and the neutron in the deuterium nucleus are held together by the strong nuclear force. What's the exchange particle of the strong nuclear force? And then the deuterium nucleus is stable. Describe how the variation of the strong nuclear force with distance contributes to the stability of the deuterium nucleus. So pause the video now, then unpause the video when you want to go through the answer. Right, so the first one is just knowledge, it's just a fact. So muons are leptons. Photon is the exchange particle of the electromagnetic interaction. The W plus boson is of the weak nuclear interaction, so it's a pion. Now remember, it's a pion if it's between quarks for the strong nuclear force, but if it is between particles, we tend to call it the gluon. The next one, the deuterium nucleus is stable. Describe how the variation of the strong nuclear force with distance contributes to the stability of the nucleus. So what you've got to do is know some key facts about the strong nuclear interaction. Firstly, it's attractive up to about 3 femtometers. Beyond 3 femtometers, it tends to 0. There's nothing there. But at very, very short ranges, close to the 0.5 femtometers, there is repulsion. So that tells us if there's repulsion close to 0.5 femtometers, it won't form there. If there's nothing holding it together as an attractive force, it won't occur there. So beyond 3 to 4 femtometers, the nucleus will not form there. But if there's attraction up to about 3 femtometers, that between 0.5 femtometers and 3 femtometers, you'll get the protons and neutrons attracted to each other and staying together as a nucleus. Next question. Tritium is an isotope of hydrogen. Its nucleus contains one proton and 2 neutrons. Tritium undergoes radioactive decay. 3 modes of decay are alpha decay, beta minus decay, and electron capture. Deduce which of these modes could produce the nucleus of another element when the tritium nucleus decays. Pause the video now. Unpause the video when you want to go through the answer. Right, so it's important that we can talk about all three decays. So what's the consequence of alpha decay? Well, alpha decay, you're going to lose 2 protons and 2 neutrons from your nucleus, because that's what an alpha particle is. So it can't occur because there's not enough material there, because you've only got 1 proton and 2 neutrons. So alpha decay can't take place. Electron capture, okay, again can't really take place because you have only got 1 proton, and what is going to go on is that in electron capture, a proton will turn into a neutron. So if electron capture does take place, you'll end up with 3 neutrons, which doesn't occur in the universe. We don't get a nucleus of only neutrons, so that can't take place either. And then finally, beta decay, that can take place because we notice it's beta minus decay. So what's happening in beta minus decay? A neutron turns into a proton. We've got two neutrons there, so we've got enough material to carry it out. And secondly, we can have a nucleus of 2 protons and 1 neutron, so it can take place. Now it's important you do know what's happening in alpha, beta minus, beta plus, gamma decay and electron capture, and think about will they actually take place. Next, we're going to look at some questions on mechanics and materials. So you'll notice here we've got a fairground rail called a reverse bungee. There are 2 identical elastic ropes which are fixed to a cage with passengers inside. The loaded cage is held in place by a clamp. When the clamp is released, the elastic ropes accelerate the loaded cage vertically into the air. Point P is the point where the rope is attached to the top of the vertical tower, and Q is the point where the rope attaches to the cage. Q is level with the center of mass of the loaded cage. Before release, the tension T in each elastic rope is 3.7 times 10 to the 4 newtons, and each rope makes an angle of 20 degrees with the vertical tower. The total mass of the loaded cage is 1.2 times 10 to the 3 kilograms, and the mass of the elastic ropes is negligible. So, show the downward force F exerted by the clamp on the loaded cage is about 6 times 10 to the 4 newtons, then calculate the initial acceleration of the loaded cage when the clamp is released. So pause the video now, and then unpause the video when you want to go through the answer. Right, so what are we going to do? So it's 4 marks here. So the first thing we need to do is understand what forces are actually taking place. So you'll notice by looking at the particular diagram that we've got an idea that we need to consider the vertical forces. So the first thing we know in the vertical is that there's definitely going to be weight. So the first thing you need to do is calculate the weight of the cage, which is going to be its mass, which is given at the bottom, 1.2 times 10 to the 3 kilograms, multiplied by the gravitational field strength, 9.81. So that's 1.18 times 10 to the 4. Now what else is acting in the vertical? Well, tension is acting in the vertical, but only the vertical component. You'll notice from the diagram that the tension, which is caused by the rope, because tension is a pulling force, so a rope or a wire will provide the tension, is acting at an angle. So you've got to resolve that into the vertical components. So you make your right angle triangle, and you realize that the vertical component of tension is going to be the resultant of tension cos 20. So therefore we've got our value of tension, but it's important to note that when we look at the diagram, there is 2 ropes attached to the actual towers, so we've got to multiply the tension by 2 because this is going to be for both ropes. So therefore we multiply the values like that, so we know F is equal to twice their tension minus the weight, so we can work that there through to get your answer to be 5.8 times 10 to the 4 newtons. Now, next, how can we work out the initial acceleration? Well, the hint I would always give you in these types of questions is, remember, we are doing Newton's laws. We've been given a mass, we've just worked out a force, we need to calculate an acceleration. So F equals ma, so A equals F over m. You've worked out F in the previous question. You were given m as 1.2 times 10 to the 3, so you can work out your answer to be 50 meters per second. So that's an important idea there. So what we'll do now is we'll move past this onto electricity. So let's look at some questions to do with electricity. A wire probe is used to measure the rate of corrosion in a metal pipe carrying a corrosive liquid. The probe is made from the same metal as the pipe. Figure 6 shows the probe, and the rate of corrosion of the wire in the probe is the same as the pipe. The wire is in an unused probe, has a resistance of 0.07 ohms and a length of 0.50 meters. Calculate the diameter of the wire when you're given the resistivity. Pause the video now and unpause the video when you want to go through the answer. Right, it's very, very important that you remember your resistivity equation and how to rearrange it. So we know that R is equal to rho L over A, where rho is resistivity. So you can firstly work out area straight away. So what you can do is you can then work out area by rearranging your equation to make A the subject. So it would therefore be, looking through, if you can work it out from R equals rho L over A is therefore going to equal rho L divided by R. So therefore you've got rho, the resistivity, in the question, you're given L in the question, and you're dividing by the resistance which is given in the question. That gets you your area. Now we also know, because it's a wire, the area is going to be a circle because it's a wire shape. So therefore area is pi R squared. So therefore you can work out R by rearranging that and double it to get your diameter. Always remember to work out either the diameter or the radius where asked for in the question, and this one's asking for diameter, so you're going to have to double your radius, and you get 9.4 times 10 to the minus 4 meters. In order to measure the resistance of a used working probe, is connected to the circuit shown in figure 7. When R3 is adjusted to a particular value in the current in the cell is 0.66 amps, calculate the total resistance of the circuit. Then the resistance of R2 is 22 ohms and the resistance of R3 is 1.2 ohms. Calculate the resistance in R3. So pause the video now, then unpause the video when you want to go through the answer. Right, so first thing, what do we know? Okay, we know that R is equal to V over I. You've been given I in the question, 0.66 amps. You've been given V, 1.5 V, so you can work it out and you get 2.3 ohms. The hint would always be it's a 1 mark question, so it's not going to be needing many calculations to work out the answer. Now the next one, calculate the current in R3. Now it's important to note that we can use V equals IR. So if we look at our particular setup here for R3, if we know what is going on in terms of R2 and R3, we can then work out what the current is going to be. So what you would say is V equals IR, so therefore I is going to be equal to V over R. So there's going to be a total potential of 1.5 volts as shown in the circuit. Well, what's the resistance going to be? Well, the resistance is going to be the two values added together because they're in a series configuration. R2 and R3 are in series. So the entire resistance of this bottom branch, this bottom path, is going to be 22 plus 1.2, so therefore you can work out the current. Now just remember, the current is going to be the same across the entire branch because that is a rule of circuits, that in one loop the current remains constant. So you would therefore get 0.065 amps. Next question. In that same circuit, calculate the resistance of the probe when the resistance of R1 is 2.4 ohms. Then calculate the percentage change in the diameter of the probe when its resistance is increased by 1.6%. Then a voltmeter is connected between points A and B in the circuit and R3 stays at 1.2 ohms. Explain without calculation why the reading on the voltmeter does not change when the cell in the circuit is replaced with another cell of the same EMF but a significant internal resistance. Pause the video now, then unpause the video when you want to go through the answer. Right, the first one you'll notice, okay, that you can work out what the current in R1 is going to be very, very quickly. And that's going to be important because we can then work out what the resistance is going to be, because then we can use this to work out complete values. So the current in R1 is going to be 0.66 amps, which is the total current we worked out before, minus the current in the other branch, because you'll notice that the top branch and the bottom branch split off from each other. So the current must be this before the branching off must equal the same as after the branching off. So if it's 0.66 amps before and the bottom one takes 0.0647, well, the top branch is therefore taking 0.595 amps. So therefore, what we can therefore do is work out the total resistance of that top branch by doing the equation R equals V over I. So what's the total V servicing that top branch? Well, we know that basically when we have branches like that, all of the EMF in goes to PD out. So there's 1.5 volts in, there's going to be 1.5 volts out, and we know, therefore, if we know what the current is, we know what the voltage is, we can work out the total resistance across the entire branch, which is 2.52 ohms. Now we already know that the resistance of one part of the branch is 2.4 ohms, so therefore the other part of the branch must have it to be 0.12 ohms. So that's an important idea. Now the next thing is, how can you then work out the percentage change in the diameter of the probe when its resistance increases by 1.6%? Well, we know that the cross-sectional area must decrease because resistance is directly proportional to 1 over area. So the area decreases by 1.6% because therefore the diameter must decrease by 0.8% because area is equal to pi r squared. So therefore, because it's a square, it's doubling in its value, so therefore when we go back one, it's going to be halving to 0.8%. Right. So, next one, explain without calculation why the read on the voltmeter does not change when the cell in the circuit is replaced with another cell of the same EMF but a significant internal resistance. Right, so when you've got internal resistance, it leads to something called lost volts. So lost volts occur because the internal resistance is dissipating some of the EMF from the power supply. So you'll get a reduced current. But that means that the actual ratio of splitting will actually be the same, because once it's actually left the power source, you're going to have the same splitting in those values. So you can see that the resistors aren't changing, so there's a constant ratio, or you could say that the voltmeter has an infinite resistance, so therefore, okay, they're not going to actually change much values because the ratios of how it splits will stay the same, even though the value will not actually change. Next question. A battery of EMF 7.4 volts and negligible internal resistance is used to power a heating element inside a glove. The heating element has a resistance of 3.7 ohms. The designers state that the battery can produce a current of 2.0 amps in the heating element for 240 minutes. Calculate the energy dissipated in the heating element in this time. The length of the heating element needed is about 0.85 meters. The designer considers using a carbon fiber tape for the heating element. Deduce whether the carbon fiber tape is suitable for making the heating element for the glove. So pause the video now, then unpause the video when you want to go through the answer. Right. So the first thing is calculate the energy dissipated. So this requires you to consider what equations you would like to use. Now for me, you can either use P equals VI, or P equals I squared R, or P equals V squared over R. Use any of the information because V is given to you, I is given to you, and R is given to you. Therefore you can then say that E is therefore equal to P times by T, and you're given T, but the trick will always be that time should be in seconds and not minutes. So you've got to convert 240 minutes into seconds. So you will get your answer out to be 2.1 times 10 to the 5 joules. Now in this next question, again, you're given the resistivity in the actual information. So what you would want to do is work out if you can make the carbon fiber tape suitable for the heating element. So you need about 0.85, okay, but what you need to do therefore is use the resistivity equation and work out the length. So rho is equal to RA over L, so therefore you can work out what L is going to be, and L comes out to be 0.91 meters. Now the important thing you've then got to do is actually give a conclusion to the question. Don't just say, oh, L is equal to this value, so therefore done. You need to actually state if they can be used. So use that information and say, could it be used, could it not be used? So you've worked out that the length of the track will be 0.91 meters and it's needed to be about 0.85 meters. So make your conclusion. Next question. A light emitting diode is used to indicate that the switch in the glove is closed. Resistor R limits the current in the LED. The figure 2 shows the characteristic graph for an LED. The circuit is designed so that the potential difference across the LED is 2.2 volts when the switch is closed. Calculate the resistance of R. So pause the video now, then unpause the video when you want to go through the answer. Right, so 4 marks, so we need to be using this graph. So what you firstly got to do is you've got to work out, okay, what particular value of potential difference you want to use. So it says it's going to be 2.2 volts from the question, because that's the potential difference across the LED. So you go up to your graph and you look across, and at 2.2 volts, it's 15 milliamps. Now we don't work in milliamps, we work in amps, so we convert that into amps. Now the important thing to note is that that's the current going through the resistor, because we can tell that because if that's the current going through the diode and the resistor in a series circuit in the same branch, therefore they're going to have the same current. So therefore we know that the current is going to be 15 milliamps. But what's the potential difference going to be of the resistor? Not the LED. Well, we hopefully remember that this is a setup of a potential divider in the sense of there's two components in parallel. So we know that the EMF supplied, which is going to be, if you look at the idea 7.4, okay, that basically it's got to split across both of them. So what you've got here is that the LED is taking 2.2, so therefore the resistor is going to take 5.2, so R is equal to V over I, so therefore it's going to be equal to giving your value 350 ohms. Next question. Figure 7 shows a circuit designed by a student to monitor the temperature changes. The supply has a negligible internal resistance and the thermistor has a resistance of 750 ohms at room temperature. The student wants the output potential difference at room temperature to be 5 volts. Now, the 0.25 kilo ohm resistor is made of 50 turns of wire that is wound around a non-conducting cylinder of diameter 8 millimeters. You are given the resistivity of the wire, determine the cross-sectional area of the wire. So the first thing you've got to do is you've got to use this, pause the video now, then unpause the video when you want to go through the answer. Right, so the first thing you've got to do is you've got to actually use the resistivity equation. Rho equals RA over L. This time we're going to make A the subject. The other trick is we need to work out L. So we can see it's a wire and it's been turned 50 times. So being given the diameter. So what you would do is you would take the diameter and you would use that to work out the circumference of the wire. So we know that the circumference of the wire is pi times by diameter, which you can see here. What we can then do is we can then multiply that by the number of turns of the wire to get your overall length, because it's been wound 50 times around the circumference. So it's going to be 1.26 meters. We can then say A equals rho L over R, so you can work out your value to be 2.1 times 10 to the minus 9 meters. Next one. In the same idea, okay, the student selects a resistor rated at 0.36 watts for the 0.25 kilo ohm resistor and determine whether this resistor is suitable. Then determine the value of R that the student should select. Give your answer to the appropriate number of sig figs. So pause the video now, then unpause the video when you want to go through the answer. Right, so what you've got to do is you've got to consider, okay, what the maximum possible PD across the 0.25 kilo ohm resistor is going to be. Well, the maximum possible is going to be 9 volts. So therefore, but you know that because the maximum possible it could take is all of the EMF. Because what's going to happen is the EMF is going to split between the top part and the bottom parallel circuit. Now the maximum the top could take is all of it. So the maximum possible PD is 9 volts. So therefore you can work out what your power dissipated will be. So we can say power is equal to V squared over R. So therefore we know from the question R in ohms is 250 because 0.25 kilo ohms is 250 ohms. So therefore the answer is 0.32 watts. So therefore that's going to be suitable because the resistor can work up to 0.36. Always give your conclusion. That's why it's very, very important to always know your equations and know how they all link together. Again, you've always got to actually state a conclusion to your answer as well. Next one, determine the value of R that the student should select. So, what do you know? Well, the first thing you should be able to use is the idea of the potential divider formula to determine the resistance of the parallel combination. So what we'd say is the potential divider equation is going to be V is equal to the R1 over R1 plus R2 times by V in, which is the input from the battery. So you can then use that to work out what the total resistance in the parallel combination is. So therefore it's 0.313 kilo ohms. What we can then do is use the equation for the resistors in parallel of 1 over R total, which we've just worked out, equals 1 over R1 plus 1 over R2. Now we know what one of the values of R is going to be because we told us 750 ohms. So we can therefore work out what the other value of R2 is going to be by doing 1 over, let's get this right, 1 over 3130 equals 1 over 750 plus 1 over R2, so you can then work out what R2 is going to be. The other way you could possibly do it is you could work out the current. So you could work out the current by doing the equation, I is going to be equal to V over R. So therefore what you would say is, R in the circuit is 250. We know that the V is going to be 4 volts at that point, because if the thermistor is 5 volts, well, the resistor at the top bit should be 4 because it splits 9, so 9 goes to 5 and 4. So therefore we know that V is going to be 4 at that point. We know what the current is going to be in the circuit, 16 milliamps. So therefore we can also work out the current in the thermistor, because we know it's going to be 6.7 milliamps by that same principle, 5 over 750 because we know the resistance, and we know the current, and we know the voltage now because they're split, and therefore you can use that to then work out your answer, again of 540 ohms, by doing the equation R equals V over I. You can know what I is because you can work it through, you know what V is because it's split across from the potential divider. Next question. State and explain the effect on the output of PD of increasing the temperature of the thermistor. So pause the video now, then unpause the video when you want to go through the answer. Right, so in this one, there's a few things you've got to unpack here. That firstly, the thermistor is in a parallel circuit. Okay, so the important thing you should hopefully remember is that when temperature goes up for a thermistor, the resistance goes down because it releases more charge carriers into the circuit. So therefore, what we can therefore say is the resistance of the parallel combination will decrease. Okay, so therefore we know that because the resistance has gone down, because the temperature has gone up, therefore the resistance of the parallel combination will go down, and because you know V is directly proportional to R, that's an important circuit law you've got to know, that if R goes down because the thermistor's resistance goes down, therefore V is going to go down in total, so therefore the output PD decreases. Remember, it's important to note that for any component that V is directly proportional to R. So when the thermistor's resistance goes down, it brings the entire parallel combination's resistance down, and therefore brings that V down because V and R are directly proportional. Right, we're going to look at a question now on periodic motion. So figure 8 shows the side view of an active formed by 2 acrobats. The acrobats, each of mass 85 kilograms, are suspended from ropes attached to opposite edges of a circular platform that's at the top of a vertical pole. The platform has a diameter of 2 meters. The motor rotates the platform so the acrobats move at a constant speed in a horizontal circuit on opposite sides of the pole. When the period of rotation of the platform is 5.2 seconds, the center of mass of each acrobat is 5 meters below the platform, and the ropes are at an angle of 28.5 degrees to the vertical as shown in figure 8. So that the linear speed of the acrobat is about 4.5 meters per second. So pause the video now, then unpause the video when you want to go through the answer. Right, it's important that you know you can and use the equations for circular motion. So the first thing we've got to know is that how do you work out linear speed? Well, V is going to be equal, if you have a look on here, you can have it as R omega is a possible one. So how can you work out omega? Well, omega is going to be equal to 2 pi over the time period. Now in the question it tells you that the period of one rotation is 5.2 seconds, so therefore 2 pi over 5.2 will give you your angular velocity. You then have to multiply it by the radius to get out your speed. Now how can you work out the radius? Well, you're told straight away that the radius of the actual platform is 1 meter, but then you need to work out the additional part of the radius of the orbit of the acrobat. So what you've got to do is look at your angles and work out from your angles what that that horizontal component of that value is going to be. So if we look at our triangle here, you can see that the horizontal section, which will form the radius, is going to be equal to tan, okay, at 28.5 times by 5, because if you think about it, tan is going to equal opposite over adjacent, and we need in this example to work out the value of the horizontal, so you can work it through to be 5 tan 28.5. You then add that 1 meter from the platform itself to give you a radius of 3.71 meters. Right, next question. Determine the tension in each rope that supports the acrobats, and then finally discuss the consequences for the forces acting on a pole when one acrobat has a greater mass than the other. So pause the video now, then unpause the video when you want to go through the answers. Right, so firstly, we need to work out what our value of tension is going to be. Now, the first thing we can say is the object's moving in a circle. So therefore, this must be a horizontal force, okay, of the centripetal force. So we can work out what the centripetal force is by doing mv squared over r. So we've got n, 85, we've got v, 4.49, so we square that, divided by r, which you've just worked out to be 3.71 from the previous question, so you get a value of 460 newtons. Now if you look at this particular diagram here, you'll notice that the only other force in the horizontal is the horizontal component of the tension. So what you've got to do is you've got to resolve the tension horizontally and equate that to the centripetal force. So we would say that the centripetal force will equal T sine 28.5, the horizontal component. So therefore you can work out what T is by taking your value for centripetal force, then dividing it by sine 28.5. As a general hint and tip, it's really important that when you see things at an angle, you can resolve them into horizontal and vertical components. So you can always think what's in the horizontal, what's in the vertical. So always practice working those through. The other way you could have done it is consider the vertical, because the only force acting in the vertical is going to be the weight, okay, which is mg, and the vertical component of the tension. So they'll equal each other. So the weight will equal the vertical component of the tension. So weight mg will equal T cos 28.5. So once again, you can work out your answer. Next question. Discuss the consequences for the forces acting on the pole when one acrobat has a greater mass than the other. Well, let's think about it again. They're moving around in a circular fashion. So therefore, it's going to be the centripetal force. Now, it's the idea that if the mass increases, therefore your centripetal force will increase, but also your weight will increase, because weight equals mg and centripetal force equals mv squared over r. So in both cases, if mass is now increased, the weight will get bigger and the centripetal force will get bigger. So therefore, you're going to have an unbalanced horizontal force now, because the centripetal force from one acrobat is larger than the other. So you'll have an unbalanced horizontal force, and you'll have an increased vertical force as well. So what will happen is it will cause the pole to bend and sway and tilt towards the more massive acrobat. Now, it's always important when you're considering forces in more than one plane, so the vertical and the horizontal, you consider both the vertical and the horizontal obviously separately, but then consider their accumulative effect. So A, we've got a bigger force on the vertical acting downwards. B, we've got a bigger force in the horizontal acting towards the more massive acrobat. So together they will cause the pole to bend and sway towards that more massive acrobat. Again, importantly as well, you've always got to relate the actual answer to the context. So you're going to have to talk about towards the massive acrobat, talk about the pole and what's going on. So that brings our revision session to an end today. So if we've been successful and learned in today's lesson, you'll be able to answer the A-Level Physics examination style questions. You can assess your understanding of A-Level Physics, and finally understand what topics we need to improve upon for A-Level Physics. Thank you very much for watching this revision session. Thank you very much, and as always, have a lovely day.